Okay, so welcome to the first pre-registration workshop in computer vision. So due to scheduling constraints, we're going to dive into the first invited talks at the start. So I'll just give you a very brief overview in case you're not sure what it's about. So the idea of pre-registration is it's an alternative publication model where papers are reviewed before the experiments are conducted. Okay, so to glance at the program, we've got 4 invited speakers. We're going to have a coffee break at 3. And we also have 3 orals, so we actually followed this publication process for the workshop. And we're also going to have a poster session during the coffee break. And then at the end, we're going to open the floor up for a discussion. Okay, so I'll introduce David Forsyth, our first speaker. David is a professor at UIUC. I tried to make a list of the topics which he's worked on. But it's pretty much all of vision, like vision, language, detection, recognition, tracking, human pose. Animation? Missed one. He also wrote the textbook, The Computer Vision, A Modern Approach, which has been a widely influential book in the field. And he was an organizer of the negative results in computer vision workshop at CVPR 2017. So thanks very much, David. We'll just switch over the laptops.
Thank you for everybody for being flexible. I managed to mix up my travel arrangements, and I'm basically going to talk and run, which is never a good thing. Oops. Oh, I know what we did. Plug it over here. Plug that back in, and we should be good. Here we go. There we go. Okay, let's get this started. So, do we need pre-registered trials in computer vision? Basically, my talk will be no, which seems like sort of a reasonable answer. But in fact, we do need a series of important related reforms. I'm here because the organizers kindly invited me. I don't make any strong claim to be a knowledgeable applied statistician. But for a variety of reasons, I had to give 2 courses to undergraduates and graduate students at my university on the sort of basics of probability and statistics and learning. And it turns out I found what was available in textbooks unsatisfactory. So you can get those now. Most universities, you can download PDFs of Springer books, and you can get those. Why do we not need pre-registered trials? Well, so if one is going to make a policy, you have to ask 3 questions. One is, what problems are we trying to fix? The other is, will the actions contemplated make things worse? And the last is, are we in enough trouble that it's actually worth acting? And you have to sort of think about those things. And we need to think about what our problems are. So the first problem, which is really worth paying attention to, is very widespread statistical and experimental sloppiness of one form or another. The next one, and in my opinion, that's worth fixing. It's annoying. Sloppiness is always annoying, but it's bad. And we'll see some of this later. The next is some or most numbers that are published can't really be trusted. All numbers come out with kind of a little bit of salt and a smile attached to them, and that is a problem. That is also worth fixing. But then there are 2 problems that I think we probably should not be worrying about. One is some papers with neat ideas don't get in. And the other is some lousy papers do get in. My experience of authors has been if you change the rules, they will change their strategies for subversion. And whatever you do, those facts will remain true. Some good papers will not get in, and some lousy papers will get in, so there is no reason to act based on that. You're just causing people to change their strategies. And we need to think about the cost of pre-registration. There seem to me to be 4. One is very significant barriers to entry, right? So if one sets it up in detail, one ends up with sort of a bureaucratic version of the I've got more GPUs than you position. Right now, most vision research is conducted on the basis of who's got the most GPUs. An alternative is vision research conducted on who's best at writing pre-registration paperwork. There's another nuisance for researchers. Should I pre-register or not? What will the reaction of the community and the referee be? And then there are weird incentives. What do you choose to pre-register as opposed to just write? Do you pre-register it because you think it isn't going to work and you can get away with it if you pre-register it, or what? And the final, and I think very serious concern, is authoritarianism. If we require that everything is pre-registered, we have to use some form of force to impose it, right? As in rejecting papers that don't do X, even if they're interesting, and that's probably not a good idea. Okay, are we in enough trouble that it's worth acting? We have some replication problems. There are real problems, and it's a bad idea to minimize them, but they're nothing like the problems that have hit experimental psychology. No word that was published in experimental psychology over the last 30 years can be taken all that seriously without some secondary attempt to replicate. We're not there. We have problems. Why? Because we publish code and data sets. And that is a really very big difference from other communities. So typically, if in the experimental psychology community, you didn't publish your data, what that meant was nobody quite knew what was going on, and they couldn't prove that you were being silly. Mostly in our world, if something doesn't work, the fact seems to become public fairly fast, and people look like fools, and that is an important disincentive. I don't think bad papers getting published isn't a real problem. I've never really known how to stop it, and I think one just has to live with it. Good authors getting discouraged or feeling that they have to do silly things to get in is a problem, and it's a problem that needs to be addressed. Okay, so what do? Well, we could look to the past for guidance, and this particular individual had one truly brilliant insight, which is rude, but he said it, not me, so you can't blame me, which is that. Right? One of the most important policy prescriptions of the 21st century. It's a very, very sensible idea. I will add to that my own subtext, which is stop other people doing it as well. How do you do that? Understand experiments so you can identify and reject papers that have lots of meaningless numbers. It's quite important to understand when a number is meaningful and when it's meaningless. Okay, so in the sort of general vein of not doing stupid things, I just couldn't bring myself. Somehow audiences inhibit me. In the vein of not doing stupid things, I want to identify some defensive statistics that everyone should but doesn't know. This is the kind of stuff that you snoozed through during the required undergraduate applied statistics course. There's probably a book on your shelf. It just, somehow never. But it's actually worth knowing. The first point of interest is significance. Here is a question. Here is a standard data set. Bigger scores are better. Mine gets 0.87. Yours gets 0.82. Question, is mine better than yours? This is an audience response mode.
You don't have enough information to answer.
The answer is who knows, right? Yeah. So, because I'm a creative type, I will do a box plot. Right? Here is a box plot of mine and yours. Do we know is mine better than yours? No. Right? Why? Because we don't know how many samples there were. And if we don't know how many samples there were, we don't know the standard error of the mean, and if we don't know the standard error of the mean, we can't tell whether they're different. This, for some reason, is a fact that is missing from our literature. Almost no published work will give you standard errors, and that's unfortunate. There is a well-known generic significance recipe, and it leads to disaster when misapplied, but it's very well worth understanding. You find a statistic, that's a number that's computed from data, and it has known distribution under random effects. You compute its value, and then you ask, what fraction of data sets would give me a number like this or worse? It could, there's some issues with positive and negative we're going to just sort of ignore. A number like this or worse, if what I believe is true. And that fraction is essentially a p-value. So I'm asking, if what I believe is true, how weird is my data set? The details have been worked out for all cases that we are likely to care about, and they should in fact be understood by our community. They do not seem to be, and there is very little practice in this area, and that's unfortunate. So you can now answer worked examples like this one. This is 1977 data about US cars versus Japanese cars, and there are different numbers of cars in each pool. You take the difference between the means, divide it by the standard error, and you get 12.95, which means they're different. Because essentially, the number of data sets that would be as weird as this if they were the same is the number of times a unit normal random variable is larger than 12, which is frankly not very often. So they're different. You can also answer questions like this, which drive undergraduate communities nuts, but is actually very like the questions that we deal with, right? 983 boys, 1,026 girls were born. Are boys and girls born with the same frequency? By the way, the answer is no, and it's known to be no, but it's not clear why. Okay. Why do we care about this stuff? Most published experiments can't be assessed accurately. Right? Why? Because there isn't any standard error and there isn't any error bar information. Usually we have enough samples where power is not, so that power is not a concern. But if you don't know variance, you're dead. For big effects, this probably doesn't matter very much. If you've got two things that are just really different, whatever. But right now, all of the effects that we see talked about are small. Significance offers very good ways to avoid fooling yourself and very good ways to fool other people, which I will talk about in a moment. Those problems are fairly minor, and we'll move on. Here is another very glaring problem with our theories of significance. We do not have a really good theory of sources of variance. So imagine you're evaluating an image classifier. You have some cutesy new trained image classifier that is better than all the other cutesy new image classifiers. You want to report a variance. The only variance you really can report is the one caused by estimation of training parameters. Now, most people don't report that, and they should. The way you report it is you do multiple test train splits, you train it a whole bunch of times, and you report the variance and the performance on the train. Of course, nobody does that because each training thing takes weeks and they whine about how I don't have enough GPUs and all that jazz. But in fact, that isn't what we care about. What we care about is the variance due to covariate shift, i.e. the pictures that you run this thing on are going to be a little bit different from the pictures that you evaluated this thing on, and chaos results. And we really have no decent theory that takes us into that area and deals with that problem. And I think it will be an important domain of experimental theory and computer vision. We really need to understand this. So the next sort of thing in the not doing stupid stuff agenda, ANOVA. So a very common question in our world is, do these factors affect the outcome? If I don't know, use residual connections or not, or skip layers or not, or whatever. And the experiment, or the recipe looks like, somebody did, this is true by the way, astonishingly, somebody at the University of Melbourne tested the dependency of pain threshold on human subjects' hair color. You can find the data set, which is astonishing. Does pain threshold depend on hair color? And the way you set something up like this, when you have one factor, is you say, look, I've got a jth experiment and an ith level. There's some mean effect. There's an effect of the choice of level. That's those t's. And then there is noise. Now, imagine nothing happens. The t's are all 0 or grouped around 0. Then what's going to happen is I can estimate noise variance two ways. I can estimate the variance by subtracting the mean from all the experiments. And I can estimate the variance at a particular level and then average those estimates of variance. And they should be the same thing if the levels don't do anything. In turn, I can test whether those two estimates of variance are the same, and if they're not, then I can say, okay, this factor is doing something and this is how much it is doing. And the answer is, again, astonishingly, A, somebody did the experiment, and B, for reasons I cannot explain, and nobody seems to have been able to explain, because I looked this up fairly carefully, people with red hair have a significantly different threshold pain threshold than people with other hair colors. Why, I cannot explain, and I believe that this is a robust result. Okay, now the reason you would care about ANOVA is you can do more than one factor. So you can set about, for example, two factors. I can say the results in an experiment with two factors are values due to a mean effect, and then an effect due to factor 1, an effect due to factor 2, and an effect due to interactions. right? So factor 1 might be the background in evaluating an object detector, factor 2 might be the lighting, and there may very well be an interaction. I set that up. It turns out this, I'm showing this mainly because I want to hammer home most of our experiments follow extremely routine recipes that have been known forever and it's known what to do about them. Right? So here is async testing whether middle-aged people are affected by age or process, or there is an interaction between age and process in memorizing words. And the answer is basically it's harder if you're older, it's harder if he uses a weird process, and if you're older and he uses a weird process, it's very hard. Now, one of the things that's kind of important there is if you look at the number of subjects, it's quite small. Why? Because if you are looking at big effects, they will be obvious on small data sets. You do not need to evaluate a significant effect on 1 million images. If it sticks out, it'll stick out on 10. Why do we care? Why do I think we should care about ANOVA? The first thing is one is forced to declare a model of effects. You say, look, this is what the factors are. This is what the outcomes are going to be, and you have to think about what causes variance. And that, I think, is good for us. It is a very good way to investigate interactions between factors, and many interesting issues fit the standard recipe. So, is an object detector affected by scale, background, and lighting? It's trivial to set up the experiment. If you've been watching me closely, that word trivial was dangerous. Why? Imagine I have F factors and L levels, and I'm going to do an experiment. Experiments take some time and trouble. Even now, they take some time and trouble. All this theory got worked out long ago. It's originally worked out for things like experiments where you plant corn and then you pick it 6 months later and whatever. So the problem when you have F factors and L levels is you could end up having to do L to the F experiments, which is hard. And in fact, in a lot of our literature, you see dedicated plotters actually doing that. It is also not a good idea. So what you want to do is choose the experiments that you do to be able to draw conclusions. And that got worked out in the 50s and 60s. How do you do it? You regress the response against factors using linear and quadratic terms. The effects are caused, you can look at effects and at pairwise interactions. That means you have to estimate 1 plus f minus 1 over 2 unknowns. But you could do L to the F experiments, and if you do, you're insane. It's expensive. So, which experiments should you do to get decent estimates of the coefficients and enough extra experiments to estimate variance and significance? Answer, Box and Benken worked it out in 1960. Here's a picture for a situation where there are 3 factors operating at 3 levels each. So these pictures, these experimental design pictures are baffling. And I'll actually walk you through it because most people haven't seen them before. So I have 3 levels, 1, 0, and minus 1 for each of 3 factors. One thing I could do is look at all 27 points, which are scattered around these red ones, plus the vertex of the cube. The one at the center is 0, 0, 0. Now what Box and Benke tell me is if I set the horizontal factor to 0 and do these 4 experiments, I do the blue one in the middle, and then I do the 4 in the center edges of the box. So 0, minus 1, and so on. And the 4 at the top, I've got enough to build a decent regression, estimate my effects, and tell significance on the effects. This turns out to be a big deal if you've got 20 or 30 factors, and if you've got a large number of layers. The nice thing about it is you don't have to think, you can just look it up. And in fact, there's Python code, although nobody seems to use it. Okay, in the final theme of not doing stupid stuff, I talked about significance and I mentioned p-values. These are a fine tool. You really can tell whether the effect you observed was due to chance. And that is something that is worth knowing. By the way, most people refer to a p-value as confirming a hypothesis. That is a logical gotcha. People who do that get thrown into the howling darkness immediately. You can never prove a hypothesis. You can fail to disprove it. It's the best you can do. Unfortunately, p-values are also a very dangerous cult, right? There are many literatures that have been poisoned by focusing on getting a p-value between 0.05, because then you get published. In some of the medical literature, it has to be below 0.025, which means you've got to fudge your experiments even harder. And I want to show you an example of how bad things can get. This is an excellent paper that everyone should have read about flexibility in data collection and analysis. So here's the result. If you listen to When I'm 64 by the Beatles, it turns out your chronological age goes down by a year and a half, right? With a p-value of 0.040, below 0.05, so you can publish it. Okay. Now, you may suspect that there's something fishy going on here, or you should suspect that there is something fishy going on here. And the only question is, what is the fishy thing? Here's how you get the result. What you do is, if you actually report everything that happened in the experiment, as opposed to the report that I showed you, you see this. The blue line points out that when they did the experiment, they actually searched stimuli for one that is helpful. So the people who listened to When I'm 64 also listened to Kalimba, Hot Potato, and they just failed to mention it. Then the other thing you do is collect data, and then the minute the data you collected hits statistical significance, you stop, which introduces a data collection bias into the experiment. And the third thing you do is you rack up as many covariates as you can think of, so that at some point, one of them is going to be helpful. You can see the covariates include mother's age, which of 4 Canadian quarterbacks believed to win an award, and how often they refer to the past, right? These are nonsensical. But if you collect them and suppress them, you can now do a search, and your search will find some significant collection of covariates and things. There's a good XKCD comment on the significance thing about jelly beans. I've actually cut down the cartoon here. But essentially, if you run a large number of significance tests and treat them as independent, you are going to find something significant. That's the nature of the thing. And that's what's actually going on in this experiment. Okay. So the nice thing about this paper is it suggests solutions to these problems. And these are solutions we should be thinking about. They are probably more relevant to us than pre-registration. So the first one is you've got to decide the rule for terminating data collection before it begins, and you have to report the rule in the article. Now, for us, that doesn't matter. Mostly the rule for data collection is we use somebody else's data set that got published. Right? Sometimes it's collected and then people work on it, but we don't usually run experiments at the same time as we collect data and stop when we hit significance, so we don't usually run into that problem. 20 observations per cell, not really an issue in our lives. We're not doing the kind of statistics that causes that problem. List all variables collected. Oh, yes, we do have problems with that. Right? Report all experimental conditions, including failed manipulations. Yes, in great big red capitals. We don't do that, and we should. If observations are eliminated, you have to report what the results are if those are included. Now, the eliminated observations are all those trial runs where the thing you did didn't quite work, and it didn't quite work because you weren't understanding it, so you sort of pretend it isn't there and do it differently next time. Right? You really should report that. If analysis includes a covariate, mostly we don't do this, but it's worth being aware of. You need to report a result of the analysis without the covariate. Otherwise, you can end up fiddling your data to look better than it is. And then he has a series of suggestions for reviewers. So there are very sensible points here. The main point is that if people actually did this, sins of omission, which are basically leaving out inconvenient facts, turn into sins of commission, which involves writing demonstrably false statements. Now, usually you can get away with leaving out inconvenient facts, but writing demonstrably false statements usually gets you into fairly hot water. And the hope is that if you impose this disclosure regime, a lot of nonsense will go away. I, by the way, think it might be quite hard to get there, but I think it's worth a try. The next point I want to point out to you is there is an argument here against pre-registration, which is roughly the argument I made, which is how do you enforce pre-registration submissions? How do you ensure that descriptions are understandably written, appropriately classified, etc.? Right? And there are real practical problems. So, two pieces of further reading. Most people here should have seen or read this Ioannidis stuff. He can get a little bit overexcited. The claim that most published research findings are false is probably better aimed at the newspapers than at our community, but it's salutary to read this. And then any number of books on applied statistics. I like mine because I wrote it, but whatever. Okay, final thoughts. 2 very good rules. Don't do stupid stuff yourself and stop other people from doing it too. And knowing really quite basic statistics with a kind of defensive knowledge of what's going on will help with both points. And that's me. And I have a few minutes before my taxi to the airport, so I'm happy to answer questions. Thank you.
Okay, thanks very much, David. I'm not sure if this is do we have any questions?
Please.
Yeah.
Yes. What we're doing in computer vision, we're basically engineering science. We are developing methods. We're not just observing them like topology. Yeah? So how does this relate, for example, if you're developing, let's say, a new kind of neural network? Yeah. You test one design, doesn't work. Next design doesn't work. Yeah. So third design, 20th design. So that's essentially what we call, the statistician would call p-hacking, right?
Yes.
And basically the whole community does that, right?
Yes, and it should. Okay, so one of the grave difficulties here is, so for much of this stuff, if the effects are really big, it doesn't matter. But if the effects are small, it matters a lot, right? So we see on a fairly regular basis claims that architecture A is superior to architecture B, where that claim has been established essentially by a search for an architecture over a fixed validation set, right? Doing what you described. That claim is unsupportable. Right? The behavior is wrong and the claim is unsupportable. People need to stop it. Right? Does that present engineering problems? Oh yes, big deal. It is a real issue, but there are civilized ways of dealing with this. And mostly they involve only actually evaluating once you're finished on a held out set that is only used then. Right? People don't do that, and the reason they don't do that is they then discover that they get clobbered by confirmation bias, and the cutesy new architecture doesn't work anywhere near as well as they thought. Right? So no, so the fooling other people is often career helpful behavior. Fooling yourself is really silly, and the behavior you describe involves fooling oneself. And that's an inconvenient fact, but it's a fact. I'm sorry.
One of the points you made at the beginning against pre-registration is that if we change the rule, then people will change the behavior to break the rule, right? And then it's not worth changing it. So, well, I would argue that if we know that a different rule is better, then we should aim for this better procedure. It's the same as we have a law, why would we have a law if that's shit? If we change it, then people will keep breaking the law and so on. Right?
So there is a long history of laws, regulations, behaviors and stuff that have been introduced to solve a problem because they were obviously better and then turned out to be a very great deal worse for reasons that nobody thought of at the time. There is an affirmative duty to prove that things genuinely will be better when you make changes in policy or regulation. Just thinking that they will be better is dangerous. I'm sorry.
So what you mentioned, one thing that there's people that really, for example, reported things that didn't work. Wouldn't something like preregistration or something similar sort of force you to do that? Because you made your plan, you're going to test a bunch of stuff, and you will report, all of the ICCV panels where something didn't work alongside the other one. And now it's clear in front of everybody. Well, when people do these big grid searches over a lot of stuff with their mammoth GPU farms, they don't really report to those. So the format does influence you to do the right thing.
So I think the tool is much more, the regulation would be much more severe than is needed to deal with the problem. So a practice, this is why I put this back, a practice, authors must report all experimental conditions, including failed manipulations. If we had that, we wouldn't need to worry too much about pre-registration. Well, the way one fixes that is a community of referees who reliably bounce authors who don't. Right? Why do we have a problem where there's this compulsive interest amongst referees in numbers? Right? Because the people who don't think that way aren't counterattacking. And the counterattack is basically your numbers are false because you haven't done A, B, and C, and you get bounced as a result. I think it's just a much more effective mechanism. Community standards are set by communities and their behaviors. Sorry.
Well, what about when they review without numbers?
I don't see much virtue in that. And the reason I don't see much virtue in that is if you think about our discipline, there's long evidence that things that look like really good ideas really don't make any difference. And things that look kind of stupid are often quite helpful. Prejudging whether they're good or bad before you see the numbers, it's unreliable. I'm not enthusiastic. I think we are better imposing stronger and more coherent reporting practices on authors than imposing rules like pre-registration.
How do we impose this? Sorry for jumping in. How do we impose this?
Reject papers that don't meet these standards.
How?
Well, I know it's fairly easy. There's a button on the referee form that says reject, and then you say reasoning, well, this guy says he's better than theirs, but no standard error is provided and no serious description of the trials, therefore the numbers can't be trusted.
That's obvious. I mean, how do we encourage the community to review papers in this way? This is
I'll start doing it. Right. So, look, the nature of a distributed community like ours is people standing up and say, you must do this, are not very effective. People actually doing things can make very significant changes. So, the short answer is, if reviewers aggressively stand up for standards, then behaviors will change.
Okay, we probably need to wrap it up so David doesn't miss his slide.
Sure, thank you.
Thank you.